So, hello everyone. We'll wait for 2-3 more minutes and then we can start. Meanwhile, if you have any questions from the previous sessions, you can ask me. Okay. So, hello everyone. Welcome to the fifth practice session of Geographic Information System. And I'm Akansha Kumari, and I'm a PhD scholar at the University of Queensland and IIT Delhi. So, if you have any questions from the previous session, please ask. Otherwise, we can start with a brief recap of whatever we have done till now, and then we can start with this session. So, in today's session, I'll focus on the querying and the coordinate systems. So, in querying, we will look how can we do spatial querying and buffer analysis using QGIS, and I have also provided steps for doing these analysis in ArcGIS also. So you can follow those, and if you have any questions, you can ask. And I hope everyone is going and practicing the hands-on session on their own. So you should practice whatever I have covered on your own. Otherwise, it is not very useful to for you to just see how ArcGIS and QGIS is used. Okay, so we'll start. So I hope I'm audible and the screen is visible. Can anybody confirm? Just write in the chat box or unmute yourself. It's visible, right? Anyone? Okay, thank you. So the course is Geographic Information System. Until now, I know that everyone knows why we are doing this course. So the main purpose of learning this GIS because it is a tool through which we can make different layers of the real world to understand the patterns that we are interested in, and this is basically what we are doing is that we are simplifying the real world into a GIS world by making different layers, and then those layers are analyzed to understand the patterns or uh, whatever information that we are interested in. Okay, So for GIS, we have two major data model types. One is vector data model. So in this we have point layer, line layer, and polygon layer. So I have also shown you how can you make these layers by manually digitizing a map in your QGIS or ArcGIS. So making a vector layer by digitizing have already been done. So if you want to learn how to do this, you can refer to previous classes. Now we also have studied about the raster data model in detail in the last session. So the raster data model basically is suitable for continuous phenomena like elevation and temperature, and it has, and if you want to show discrete feature you should use vector data model. Like if you want to show cities, you can use point layer. If you want to show roads or river network, you can use line layer. And if you want to show a lake or a city boundary or a state boundary, you can use polygon layer. So I hope till this everything is clear. Then we moved on to querying. So querying is basically asking questions. Uh, so it is basically filtering based on the attribute or spatial relationship. So there are two types of querying that we talked about in the last class. So first is attribute querying. So actually three types. So first is attribute querying. So in this we use attribute table, and based on the features in the attribute table we can do querying. Second is spatial querying. So this is based on the geometric relationship, like how much distance is something from a place that we are interested in. And then combined querying is combining both attribute and spatial querying. So for this, I talked about an example of suppose if you are hungry, then you want to look for restaurants that are nearby. So you can look for restaurants that are within 5 kilometers of your location. Okay, so within 5 kilometer distance. So that particular type of filtering or querying is spatial querying. Suppose you are interested in a vegetarian restaurant, then the attribute of the restaurant should that is that it should be vegetarian. So you will look for both the attribute and it should be within 5 kilometers. So this is both attribute and spatial querying. So querying is basically filtering. Okay. So then we talked about attribute querying in detail. So for doing this attribute querying, you need to know the structure query language. So this is the language that you use to communicate with the databases. Okay, so this is called as standardized programming language used to communicate with the databases. Okay, so in the last class we did how can we do attribute querying uh, in QGIS. Now we'll move on to spatial querying. So spatial querying is basically done to get a geometric or identify geometric relationship. So the core relationship can be these kinds, like intersect, within, contain, touches, overlap, or nearest. So that is basically dependent on the location. So that is why it is called as spatial querying. Okay. So suppose if you want to know how many villages are within the flood zone, so this type of querying is spatial querying. So you can see if this is the flood zone, you will see which villages fall into this flood zone area. Okay, so this is spatial querying. So these are the steps that you can follow if you are using ArcGIS, and these are the ones that you have to follow if you are using QGIS. Okay, so what I'll do is that I'll use QGIS to show you how can we do spatial querying. Okay, so what do we need? We need some layers that we can analyze, right? So I'll add some vector layers so that we can analyze those. So I'm adding vector layers. So I think these should be sufficient. So these layers you can make after georeferencing a map and then digitizing them. Okay, so and I'll also add Indian boundary so that you can know which area we are looking at right now. So if you want these layers, I can also upload these layers like India boundary and some shape files, point vector um, in the Google Doc. So if you want that, you can message right now. Okay, so that I'll upload these and you can do these analysis on your own. Okay, so you can see this is the Thar Desert region, and this is extent of Thar Desert when 16,000 years ago. Okay, so this particular polygon is that one. Okay, and we have added India boundary also and some settlements. So late Harappan settlements and early Harappan settlements. You can see this is late and this is early Harappan settlement. So now what we are interested in? We are interested in okay. So what we are interested in? We are interested in spatial querying. So one type of spatial querying is determining the intersect. So we can look for all the so suppose this is the desert extent. So how many of these settlements lie in within the 16K Thar desert extent? Okay, so these kind of querying we can do. So let's see, we can go for early Harappan and then so first you have to choose which files we are interested in. So if we are interested in early Harappan, then I'll just remove this one and you can go to early Harappan input layer and then go to the attribute table. Okay, so here the attribute table is Mm, like it doesn't have, it only have the IDs. Okay, so maybe, so let's see. So last time the layer we used, it had ID and some values also. So then using this expression was easy as compared to for this layer. Okay, so maybe I have to change this layer. So the attribute layers, actually this layer we made after digitizing. Okay, so we are the ones that have to make the attribute table. So there was no ID assigned when we were digitizing. So that is why it only has this feature, only ID, not other features. Same for this one. But if you add a layer by making a CSV file, so if you have like all the latitude and longitude values, then the name of the settlement and then everything written, and then if you add, then your attribute table will be like complete. It will have all the columns. So because this was kind of um, made by us after digitizing, that is why it doesn't have. And also if you see here, the reference system is also like not assigned. So this you can see, whenever this icon appears, then that means they have, it has no projection specification. Okay, so what QGIS does is that it takes the geographic coordinate system um, as coordinate reference system as its coordinate. So basically this particular projection is used. Okay, so it assumes that whatever lat long was given is in geographic coordinate system. Okay, so that is why this is coming out to be at the same place as we expect, because all the referencing we do in is in geographic coordinate system, right? So everything was in decimal degrees. But for this layer, we have to specify uh, like if you want to do analysis, you have to specify which coordinate reference system is this. So you can just go to layer or go to vector. There is somewhere wrap projection. We can search this. You have to go and change the projection, set the projection. So we can go and reproject layer. So we have to find this one, reproject layer. Okay. Okay. So in data management tool, go to reproject layers and then you can run this. Okay. So this is the reprojected and this is coming out to be at the same place because we have reprojected to WGS 84 only, so the geographic reference system. Okay, so that is why the attribute layer is not coming out here. Okay, so for doing, we'll remove the reprojected because right now it is coming out to be at the correct place, so we don't have to worry about this. So we'll go to the vector because all the layers are vector layers, and then go to research tools and then select by location. Okay, so here we'll change this to early Harappan. Okay, and you can see all the features. So these are the ones that were uh, listed with for the spatial querying, right? Intersect, contain, disjoint, equal. So these are the ones uh, that we can use. Okay, and then we can choose data, and then we can run this. So now if you close this, you can see whatever settlements were in this, like within these, this particular extent, 16K extent is now appearing to be highlighted. Okay. You can also like create a new layer out of it. So you can modify the current by creating new selection, adding to current selection. So these are the things that you can do. Okay. So now you can see these are highlighted. So this is called as spatial querying, and these are the things that you can do: intersect, within, contain. Now in spatial querying, you can also do buffer analysis. So you can see, create a buffer around any layer and then see what are the things that are coming or how much distance. Like by creating a buffer zone, you can do spatial analysis. Okay, spatial querying. So we know what is combined query. So using both attribute as well as spatial querying. So we'll not do this because our layer doesn't have attribute for now, and we did this in the last session. So I hope this was clear. Now what you can do, For raster, you can also do querying. So suppose if you add a raster and then you can choose the areas which has elevation greater than 800 and the vegetation index if you have plotted. So the points that has less than point 0.2 uh, point 0.2 veget NDVI. So these are the things that you can, and for rainfall you can look at the extreme events where that is happening. So where the standard deviation plus minus 2 is going. Okay. So these type of querying you can do for using raster data. So and these ones are for vector data. So for doing raster querying, you can see, these are the steps. So for QGIS, you can go to raster calculator and then write this. So maybe we can add a raster layer and see. So we have elevation data for this particular region. Okay. So we'll zoom to this layer. So for this region, we have elevation data. Okay. So if you want to do raster querying, first you have to go to raster calculator. Okay. So go to raster calculator and then we have to write this should be greater than, we can choose a value, maybe 3000. Okay. And then we can set an output layer. Okay. And then click OK. Okay. So now you can see the areas which had uh, so this is like a logical expression. So whatever is below, like whatever is greater than, our expression was elevation should be greater than 3000. Okay. So whatever values or whatever raster is having that uh, that true, like the elevation, the areas where elevation is greater than 3000 is appearing 1, so it is white, and the cells for which that particular expression was not valid, not true, so that is appearing to be 0. Okay, so you can see all the lower elevation values are 0 because they are less than 3000, and other ones that has higher values are having values 1. Okay, so this is what happens when we use this analysis. So you can check, set a threshold. So you can set a threshold and see whether this is followed by a particular cell or which cells are following this type of expression or not. Okay. Okay, so which process, this raster querying process? Okay, so yes. So this squaring, through this squaring, what we do is that we uh, make a expression, and for that, suppose this is for a raster data. So I have added a digital elevation data for an area. Okay, so you know the values are ranging from 0 to 5,000 something. Okay, so first you have to go to raster and then go to raster calculator. Okay, and now we'll choose this because this has the value of elevation, and now I'm choosing it will be this elevation should be less than 3,000. Okay, so now our logic is that elevation give me the area where the elevation is less than 3,000. Okay, and now if I click OK, so if you see this, the high and low elevation, they are kind of opposite to each other. So this is called a Boolean expression, and from the logic that you give, if that logic is true, that means it will give a value of 1. So all the elevation areas that are less than 3,000 here are having value of 1, and others are having value of 0, because the expression is not valid for these cells. Okay, so that is why this low elevation and high elevation is kind of opposite to each other, because in both of them, for the high elevation I chose that the elevation should be greater than 3,000, and for the low elevation the elevation should be less than 3,000. So one is appearing when the expression is valid. Okay, so for each cell it is calculating whether that expression is valid or not, and if it is valid it will give a value of 1, if it is not valid it will give a value of 0. Okay, so this is how this raster querying can be done. So you can set a threshold and then see how many cells are satisfying that particular threshold. Okay, and if you are using ArcGIS, you have to your SQL is going to be something like this. So elevation 800 10. So if it is valid, then it will be 1, else 0. So this is what is done here also, but how you write the expression is going to be different in ArcGIS and QGIS. So always check like how the expression is written in ArcGIS, how it is written in QGIS. Okay, so now I'll move on to the buffer query part. Okay, so buffer is basically a zone that is created at a specified distance around a feature. Okay, so suppose you have a point layer. So what happens? Your buffer is going to be circle, right? Because you will see like within 5 or 10 kilometer which areas are falling within that. Okay, so what is the goal of creating buffer? So suppose we want to select features that are within a particular distance from another feature. So what we do, we create a buffer around that and then see which features are falling within that. Okay, so let's see. So for example, what you can do, what are the areas that are within 10 kilometers from a river? So this can be very useful if you are trying to see a flood zone area. So whatever area that is within this kilometer are going to get affected from flood. Okay, so that is why this kind of analysis is done. So you can see this is a visual example. So suppose this is the river. If you create a buffer around the river, then what happens? You can see which are the zones that are going to be. So these are the flood affected zones or red zones that get affected by floods. Okay. So this is what we will do. So for ArcGIS, you can um, follow these steps. So you can create a circular buffer around point layer, also buffer around line layer and polygon layer. Okay. So for QGIS, this is what we have to follow. So first we need to select. So first we need to select which feature are we interested in. Okay. So suppose I'm interested in this desert extent and I have to create a buffer around this. So first of all, we will check the coordinate system. Which coordinate system is this in? So whenever you are interested in area or any calculation, you always have to project the reference system, uh, reference system. So because if your reference system is in decimal degrees, so geographic coordinate reference system, then you cannot calculate the area or distance or volume, whatever. So always if you have to calculate anything, you have to change the projection coordinate reference system to a projected reference system. Okay, so you can see this is WGS 84. So this is geographic coordinate reference system. So all the values are in decimal degrees. Now for creating a 5-meter buffer layer, first we have to change the coordinate system. Okay, so for that what we have to do, first go to properties and then go to source, and you can see the coordinate system. So this is a geographic one. Now you can see here it has been written that if you change the coordinate system from here, it will not change the CRS, coordinate reference system. Okay, so you have to reproject this layer to change the uh, reference system. Okay, so we'll go to vector and then go to data management tool and then reproject layer, and now we have to change this to a projected one. So this is now, so always check the units. So now the units are in meters, right? So now it is correct. Now the units are in meters, so we don't have to worry about it. So now run and then okay. Okay. So now this is reprojected layer. So now we will use this for creating a buffer. Okay. So now for creating buffer, we have to go to vector again. So all the analysis for vector will be done from this. So in QGIS it is like separately written for vector analysis, like for vector files you have to go to vector. For raster you can use these tools. Okay. So go to vector and then geoprocessing tools, and then you can see we have lots of options: buffer, clip, difference, dissolve, intersection. So lots of things are there. So we will go to buffer, and then how much distance are we interested in? Maybe 10 kilometers. Okay. So you have to select um, the input layer. So we'll always use the reprojected layer, right? Because uh, here the units are in meters, so it will be like good for calculating. Okay, because in buffer analysis the calculation is very much important. Now the distance is going to, you have to select what kind of buffer you are going to uh, so like what is the buffer uh, width. So that is going to be 10 kilometer from the layer. Okay. Now dissolve result. You can either select it or not select it. So let us run and see what we get. So let's see. So if you see, this is the reprojected one. Okay, the extent. And now after buffering, there is a 10 kilometer buffer around this layer. Okay, so now you can see the buffer analysis has been done. Okay, so this is buffered layer. Okay, so this is how you can do buffer analysis. So this was done for polygon. Similarly, you can also add another, like a line shapefile, and you just have to follow the same steps. Okay, you just have to go to vector data management, sorry, geoprocessing, and then buffer, and then choose that, and then choose the distance, and then run. So steps are basically same, and you will get this. So let us see if now I'll show you if you don't change the coordinate reference system, what is going to happen. Okay, so let us assign a geographic coordinate reference system to this, and then see what happens. So go to vector. Earlier happened. So now you can see this is unknown. Distance, the unit of the distance is unknown. Okay, now if you run this, close this, and if we zoom to this layer, you can see this is what has been drawn, because the units of this feature was not known, so this is how the buffer was created, and this is not correct. Okay, so always keep in mind that your coordinate reference system should be correct. So now what I'll do, I'll reproject this layer, and we'll see. So we'll reproject this first to this. Okay, and then again reproject this, because this for this the coordinate reference system was not known, but we know it is what? Geographic one. Now if you have assigned that this is a geographic coordinate system, then you should do the reprojection. Okay. So again reproject, and now we will reproject it to something uh, that has units in meters, and then run. Okay. And now you can do this buffer analysis. So now you can see this is the layer that has been reprojected, this one, and now the units are in meters. So now if you run this, close this, just not. So because that was in meters, 10 meters, we forgot to do it for kilometers, so we are not able to see it. So I'll just remove this layer and then again do this. So this should be in kilometer, otherwise you won't be able to see this. And now if you see, the buffer has been created around the settlements. Okay. So so the most important thing was what? Always reproject the coordinate system so that the units are in meters before doing this buffer analysis. Okay. So I hope this is clear till now. Any doubts? So if you don't have any doubts, we can move on to the next part. So we'll take a 5-minute break, okay? And then we'll start with this part, coordinate systems. And right now, like up to this part or from previous session, if you have any doubts, please ask, okay? So for this querying also, your georeferencing should be correct, and if your control points are not within, like, okay, so there are some questions. So can you explain why the ungeoreferenced layer had the point data at the correct location? Okay, so even though it was not, so suppose even though we didn't have had any information about uh, where, like, what is the unit up to which you want your buffer layer to be, but always it will be buffered around your exact points. Okay, so it doesn't it will not depend like whether you know the units or not. Okay, and in QGIS what happens, and also in ArcGIS, if your layers reference system is not known, it will assume it to be geographic reference system. Okay, so I hope this is correct, or you understand it. So what it was doing is that it was assuming it to be a geographic reference system, okay, and then it was creating a layer around that point, okay. So even though the units was not known, it was assuming it to be some degrees, okay, so maybe 10 degrees. So let us do this projection one more time for early Harappan, and then see if it is doing creating a buffer of 10 degrees or not. So that will kind of uh, prove that it is assuming that our layer is uh, georeferenced. Okay, so our layer is buffered using a 10-degree value. Okay, so let's see. Now if you zoom to this layer, and suppose this is the point, so it is kind of around 22, and this is 22.28 maybe, okay, and then this is coming out to be 15 at 10. So I'm not sure how these units are coming. Okay, this is 33, this is 22, and this is 11. Yeah, so this is kind of 10 degrees or 1 degree, no, 10 degree, 33, and then if you come here it is around 22 or 23, and then here it is around 13. So it is assuming it to be geographic coordinate system, and then buffering, creating a buffer of 10 degrees. Okay, but we want the buffer of 10 kilometers, so that is why we need to uh, reproject it. Okay, so I hope that was clear. And so can you message if that point was clear or not, or this was the question which I have answered. So you can create uh, like both. the inward and the outward side also. So you can there is a option of negative. If you make the distance to be negative, so it will create buffer inside. So right now it is creating buffer outside. You see this. It has gotten location details. So can you unmute yourself? Because I didn't get this question. Georeferencing is used for raster or for vector. So I think you are talking about a geographic coordinate reference system, not georeferencing. Yeah. So if you are talking about geographic coordinate reference system, so for that the units are in degrees. So latitude and longitude are in degrees. So you can see these are in degrees. So those are basically what we usually provide for creating shape files or maps, or when we do georeferencing, we use that value only. But for doing calculation, like if you want to calculate area of this polygon, or if you want to calculate distance of this point to this point, so that particular calculation you can only do if you project your 3D data into a 2D map, right? So that is why we need to do this projection, so that we have uh, the units in meters, and then if the units are in meters, then you can do this calculations, right? So that is why we need to convert from geographic coordinate systems to this projected coordinate reference system. Okay, so I hope this is clear. So when we do georeferencing, so you're right, when we do georeferencing, we provide the details in decimal degrees. So both are in degrees. So latitude and longitude. So that gives you kind of 3D information about the data. But while we like do calculation, it is very important that your units are in meters. Otherwise, you know what will happen. It will create a buffer of 10 degrees, and you wanted your buffer of 10 kilometers or 10 meters. So this is what happens. Okay, so always check the coordinate reference system and then reproject it if you need that. Okay, and Sagar, you can create buffer both, like inside and outside. So if you take your value, so I have also written it here. So can buffer inside negative distance or outside. So if you take a negative distance, then it will create a buffer of like inside buffer, and what we created was outside buffer. Okay, so was that clear? Okay. Okay, so this is something that we are going to like revise one more time. So coordinate system. So basically you can see this is 3D um, 3D representation of all. And for our reference, we have made these latitudes and longitudes so that we can refer to any location in in a 2D map. Okay, so what we do in geographic reference system, we use latitude and longitude values, and they are in degrees. Okay, so this is what we call as geographic coordinate reference system, and the other one is projected one. So in the projected coordinate system, these coordinates are on a flat map. Okay, so what you are doing, you are converting the 3D data into a 2D data. So you can project it in different ways. There are lots of different projection, but even though there are different kinds of projection, when when you calculate the area or distance or buffer, then the value is going to be the same, because based on the projection, like the software knows that in this kind of projection, this particular, like, this is how we can calculate the area or distance or buffer. Okay, so always we have to, so this geographic coordinate system is very good for storing data, because you only have like these two values, latitude and longitude, but it is not good for measuring areas or lengths directly. So we saw, like, while we were creating buffers, if the coordinate is geographic, then it was making a buffer in degrees, so that was not good. So always we have to project it on a flat map and then analyze area or distance or create buffers. Okay, so you already know there are different ways through which we can project this, and you can see these, this is the one that is kind of very popular, cylindrical Mercator. So this is the usual maps that we see, and this is conical map, so this is good for high latitude areas, and this planar one is good for the polar areas, representing the polar areas. Okay, now, like, in each projection there is going to be some kind of, because you are making a 2D map from a 3D map, in each projection there is going to be some kind of distortion. Okay, so if you follow this particular projection, so Albert's equal area conic projection, so in this kind of projection, these ones, what happens, we have equal area concept, so the area is going to be preserved. Okay, so what happens, you can see this is circular, kind of circular in between, and as you go high latitude, this is becoming elliptical. Okay, so here what happens, the even though the area is preserved, the shape is going to distort. So whatever shape was in the high latitude areas, that is going to get distort. Okay, so in this kind of projection, what happens, your area is going to be preserved, but shape is going to distort. Okay, so in equidistance, what happens, it preserves distance from a point or line, so correct distance from center or standard line, but what is the consequence of this, distance is not preserved everywhere and the shape distort. Okay, so from a standard, like, uh, center or standard line, the distance is correct, but within like 2 points or some like other points which are not the center point or standard line, the shape or area is going to change and the distance is not preserved. Okay, so the distance is true from the center. So whatever distance is there from the center is correct, but the distance between these 2 points are not correct. Okay. So it will be correct if you calculate using QGS, but just by looking at the map, you cannot make out what is the area. Okay. So I hope this is clear. Now, the other type is conformal. So in conformal, it will preserve angles. Okay. So these are the examples, different examples. So what is the advantage of this? So this is great for navigation, wind flow direction, because the angle is going to be correct. But the limitation is the area explored, like the Greenland is going to look very huge in the Mercator type, and distance varies a lot. Okay, so in conformal type, if you are exploring, if you are interested in knowing the directions, then this particular conformal type is good. But if you are interested in, like, just visually, if you are interested in distance and area, then this is not correct. Okay, so this is how the conformal concept looks. Okay, so this is basically the Mercator one. So you can see the here the area is increasing as you go away from the equator, the area of the circle is increasing. So that means here whatever features you are looking, they are actually bigger in the map than in the real world as compared to this one. Okay. Now, then there is one balance aesthetic which is compromised. So this is Robinson or Winkle Triple or Natural Earth. So looks right, balance distortion, and this is very popular in atlases. But here nothing is preserved. So in this one, what happens? We try to balance everything. So even like area, distance, and angles, everything we want to balance, but actually nothing is perfectly preserved, but still it looks like balanced. Okay, so this is a compromise concept. So this is like every area is moderate and shape distortion is also kind of everywhere, but it is kind of balanced. Okay, so you can look at this cheat sheet, projection selection. So if you want to preserve angle, you will go for conformal. For preserving area, you can go for equal area. Preserve distance, equidistance, preserve direction, azimuthal, and then balanced is compromise. So Robinson and these natural earth. So these are the ones that you can look for. Okay. So the main thing is from here what you can get is different kind of projection are going to look different on a map, but even though they are going to look very different on the map, so you can see these are the different types. This is cylindrical one, this is a conical projection. So you can see for looking at high latitude areas, this is going to be good. Polyconical means instead of one conical area, we are looking at a polyconic area. Okay, so scale is true along each parallel and along each meridian. So along each parallel the scale is correct here in this one. And for this one, in conical projection, what happens? For this particular uh, zone, the distance and areas are going to correct. So this is limited. The correct information is limited to a single portion or limited portion of the map. Okay. So even though these are like different projections, when we do calculation using QGIS or ArcGIS, if it is in projected coordinate reference system, the area or the distance it is going to be correct because the software knows which projection is this and how the distance or the area can be calculated. Okay, so that we don't have to worry about. But if you are interested in visually looking at area or visually looking at distance, then you should go for this cheat sheet. Like if you want to preserve the direction or preserve the shape of the uh, different states, then you should go for these ones. Okay, so I hope up to this everything was clear. Okay, so let's move on to the next part. So data quality and errors. Okay, so what happens, there can be multiple sources from which the data sets can have some errors. So we have to determine um, what, like how reliable the results are. So for accuracy, we need to have positional and attribute accuracy. So positional means how the coordinates are close to the true ground location, and this can be corrected using which technique? Can anyone type? Which technique is going to be useful to correct positional error or increase positional accuracy? Anyone? We have already done this. Closeness of coordinates to true ground location. No one knows what technique we use to correct the reference system or align the coordinates of a map to a true ground location. You can answer in the chat box. Now, out of these two, digitizing or georeferencing, which is the one that is going to, yeah. So now you know it is georeferencing. Okay. Now for attribute accuracy, that means your descriptive data should be correct. Okay. So if you remember, after digitizing, we didn't have attribute table. So we can also like make attribute table, correct attribute table by making an Excel sheet. Okay. So this description also should be correct. Then the precision. So that means the detail, or if a GPS data is giving up to like 6 decimal places, that means that it is very much precise in giving the location. Okay, and consistency means if you are creating a polygon shapefile, then it must be closed. If you are making a river uh, shapefile, the river should not go uphill. So that kind of logical consistency should be there. Completeness means it should be all the features should be present, and timeliness means the data should be up to date. Okay, so these are different dimensions of data quality, and then there can be different kinds of errors, so random, systematic, or gross error. So gross errors are basically introduced by human mistakes. So suppose if you digitize a wrong feature or mistype an attribute, that kind of error is gross error. Systematic error is a consistent or repeatable error, and this is due to instrument or method. Okay, so suppose if you use any old map projection that has not been updated or corrected, so it can introduce a systematic error. Then there can be some random errors. So random errors are very unpredictable variation. So like suppose your GPS signal is affected by atmospheric condition, then that type of error is random error. Okay. So, what are the sources of error? So, instrumental error, human error, data capture. So, there can be scale or resolution mismatch or issues. Then, processing. So, while processing, there are some assumption that the model does. So, that can also introduce some error. And then, in conversion. So, suppose if you convert from raster to vector data, there can be loss of precision that can happen. Okay, so these are different sources of error. So at each step we have to be like very careful. Now measures of spatial data quality. So for this we have to look for positional accuracy. Horizontal accuracy means XY coordinates of feature should be correct. Vertical accuracy means elevation of the data should be correct. Then temporal accuracy means timestamp should be correct. Okay, so example is suppose a GPS is supposed to be at 100, 50, but it records 100.5, 50.3. So what is the error in distance? So how you can calculate this? 100 minus 100.5. So 100.5 minus 100, this is zero point 0.5, and so x delta x square plus delta y square का under root. Okay, so you have to you can calculate the error in the distance. Okay, and this is coming out to be 0.58 units. So this is how, like, when even when we do georeferencing, if that particular error residual error is greater than the resolution that we are aiming for, then we will remove that particular control point. Okay, so this we know georeferencing and digitizing. So georeferencing is basically aligning the map with actual geographical location, and digitizing is like after doing georeferencing only you can do digitizing. So the map that you are digitizing should have correct geographic coordinates, and then by manually tracing it you can create vector data like point, line, or polygon features. So this is called as digitizing. Okay, so you know the difference between georeferencing and digitizing, right? Now, georeferencing, the error that I was talking about is this one. So if suppose your source control point is somewhere here, and after doing the transformation, the control point is coming out to be here, then it calculates the errors. So if you remember in QGIS, you can see the errors itself, okay? And if your error is very large, then you will discard that point. So if RMS error exceeds the spatial resolution, then you will discard that ground control point, okay? So you will look at some ground control point, then transform it, and then resample to the new grid. Okay, so this is what we do in georeferencing, and I hope like you know well and you have practiced by on your own how you can do georeferencing in ArcGIS and QGIS. Okay. Okay, so for checking the positional accuracy, what you will do, go to the link table and check RMS error. If RMS error is exceeding the resolution that you are aiming for, then you will remove that control point. Okay, otherwise we will keep it. So for positional accuracy, you know where to check for the error values. Okay, so if you see here, while doing georeferencing, you can see dx, dy, and this is the RMS error residual. Okay, and if these values are very high, you should discard it. Okay, so what can be the factors that can affect the accuracy? So mismatch between the data set, spheroid or datum, then the map projection, if they are distorted, then it can affect the accuracy. Then while surveying also, like your instrument and method, if you should always check whether your, like, which is the reference system that the instrument is saving the location. Okay, media stability, so suppose you are using a paper map, so that like all the maps in the papers, they can either shrink or expand, so that can also give error, and you should georeference it or correct it. And digitizing, so if you hand trace it, you always have to zoom in and then trace it, otherwise you can introduce large amount of error. And the instrument that you are using, it should be like precise, so instrument resolution also affects accuracy. Okay, now moving on to the second type of accuracy, which is attribute accuracy. So attribute accuracy means correctness of feature description. So for example, if a polygon that is tagged as a forest but actually is an agriculture. Okay, so always you have to check the attribute table if if the correct polygon is assigned correctly. Okay, so if you want to check your attribute accuracy, what you can do is that you can open the attribute table and add random points. So create random points and then export that random point to Google Earth, and Google Earth is going to provide you ground truth. So you can check whether these points are matching with the ground truth or not. So you can check for the accuracy. If the correct matches are high, that means your accuracy is going to be high. Okay. So same thing can be done here also. So in QGIS also you have to do the same thing. Pin attribute table, use SCP file, and then do these analysis and then calculate the accuracy, attribute accuracy. Now the next type is thematic accuracy. So thematic accuracy means classification, whatever classification you have done for the data, that also should be uh, correct. But these classifications are never perfect because raster data that you are using is providing a like average condition of this pixel, so that classification is never going to be perfect, but still the error should be quantified. So there can be different error types. So commission error, so extra pixels can be wrongly assigned, so false positive. Then omission error means true pixels are missing, so this is called as false negative. And then there is confusion matrix or error matrix, so compares error matrix should be compared classified pixel with the reference data. Okay, so there are different measures of accuracy, producers accuracy. So what like actual whoever is providing the data, how much error is there in that one, then user accuracy, then overall accuracy, and then you can calculate some statistic so that you can measure the accuracy. Okay, so these classifications are never perfect, but error should be quantified. So since we are talking about thematic accuracy, we should know how can we make this classification. Okay, so you can only understand this type of errors and accuracy type if you have some classified data, right? So for that, first of all, you have to make color composite, and then only you can make land use land cover classifications. Okay, so what I'll do is that I'll show you how can you um, make color composite using raster images in QGIS. And for ArcGIS, these are the steps. So in the next class, I can show you how can you do these steps in ArcGIS. But for today, we'll see how can we make color composite in QGIS. Okay. So let us. So for making color composite, you should have Lancet data downloaded. So you know from where you can download, you can go to USGS website and download the Lancet data for for any region of interest, right? So after you have your data, suppose you downloaded Lancet data, you should always check the combination. So suppose I downloaded Lancet 8 data, I should always check the Lancet 8 band combination. Okay, so what it means that which band is which particular wavelength range. Okay, so here you can see band 1 is coastal or aerosol, band 2 is visible blue, so it covers the visible blue range of spectrum. Okay, band 3 is visible green, band 4 is visible red, and band 5 is infrared. Okay, so this kind of information you should always check. So suppose if you download any other data like Sentinel-2 data. So always check if, what is the band information or band combination of that particular data set, because in every different type of satellite the different band numbers correspond to different wavelength ranges. Okay, so always go and check this kind of information. Okay, so we'll remove this. And first of all, so if you don't know how to download the Lancet 8 data, you can go to previous lectures, and I have shown how can you download USGS. Uh, you can download the Lancet 8 data from USGS website. Okay, so just download that. And this data I cannot provide because those are very large data sets. So it's difficult for me to provide that in Google folder. So I'm adding band. So I have downloaded the Lancet 8 data. You can see LC08, and I'm adding different bands. So B6, B7, B8. Okay, then add and then close. So now you can see different bands are there, and we can just zoom in to the layer. Okay, okay. So if you remember, B2 was what? Blue light, right? So what I will do is that, and this is B2. B3 was green, B4 was red, and B5 was what? Infrared. Okay, so we know the band information. Now for making a color composite. So color composite means what we are doing is that uh, from this band we want to see we can make a true color composite or a false color composite. True color composite uses the red, blue and green data. So our eyes, like whatever we see, what like if you want to see the true color that we see from our eyes, you should check the red, green and the blue band data. Okay, so what I'll do is that I'll add satellite data, like satellite base map, Google satellite, so that you can see. So this is what we are seeing. Okay, and if we make a true color composite, our composite is going to look like this only. Okay, so first of all we have to import the data and then load the bands. So all the bands has been loaded, and now we'll go to semi automatic classification plugin. So this particular plugin should be installed. So you go to plugin and manage and install plugin and search for semi automatic classification plugin. Okay, So this plugin you have to install. Okay. So this is installing this particular plugin. So you can see the description. This is very useful for supervised classification of the data. Okay. So now you can see this particular doc will appear. If it is not appearing, you can just go to this particular uh, icon and click this. And now you can go to band set, and then you can add all the band data. Okay. So we'll select all the bands. Okay. And now here if you go to wavelength, you can see we have lots of options. So if you have downloaded Modis data, you can select this. But we have downloaded Lancet 8 data. Okay. So we'll select this. Okay. And then you can create a virtual raster and then run this. So now this is creating a stack of all the bands that are there. Okay. So from that stack, you can see we are creating a virtual raster of band set and creating raster of band set stack bands. So we are stacking all the bands in a single layer. This is what we are doing. Okay. So I guess this is done. Okay. So that was not added automatically. So we'll just go to that particular folder and add that. So now you can see here this particular file has been created. We'll just open it, add it, close. Okay. So right now you can see we have three colors, red, green and blue, and we have lots of bands from band 1 to 11. Now what we will do here, we will assign the true color. So for red band, we'll assign for red color we will assign the red band. So it was 4. Green was 3 and this was 2. Okay. And then we will apply this and then okay. And this is appearing little bit darker. So maybe we can just zoom in. Wait, this is not working. So this is basically you are assigning a true color. So it will appear similar to um, the one that is in the background, so Google satellite map. But this is right now appearing to be darker, so we need to do enhancement, contrast enhancement. Okay, so contrast stretching we need to do. So this is what I was trying to do, but this QGIS is not responding. So till that we will go to the false color composite. So in false color composite we are assigning false colors to the red, blue and green data. Okay. So what we are doing for the red color we are assigning IR, IR band. For the green color we are assigning red band, and for the blue color we are assigning the green band. So what happens, this is done because in the false color composite what will happen, all your vegetation will appear red, because vegetation is very much reflective in the IR range, and your ocean and water bodies will appear as blue. Okay, so you can easily identify the vegetation, easily identify the water body. So that is why this false color composite is created. Because this is very heavy, these satellite data are very heavy files, this is not responding. But I hope the concept is clear, right? So if you have any questions you can ask while I'm struggling with the no response from the QGIS. You can just write in the chat box. Any questions? So this particular toolbar that I have added, raster toolbar, like it can automatically stretch your data so that, like, right now this layer is appearing darker, a bit darker. So it will do contrast stretching so that your layer is visible. Okay. Uh, I'm just closing this. So any doubts till now in this part or any part? So right now I'm adding raster toolbar, and I'm also adding that file that we created, stacked file of all bands. Okay, and now what I'll do, I'll just zoom into some area. Suppose this is our area of interest, and then again this is not responding. Okay, so there is some issue with QGIS right now, but in the next class what I'll do is that we'll make a false color composite, and also again I'll make true color composite and show you that it matches with what the satellite data shows. So it is a true composite of the all the bands, and in false color composite you can easily identify your water bodies and vegetation. So that kind of information we will get, and then I'll try to show this using ArcGIS also. Okay, and right now, if you have any doubts, you can just message in the chat box or unmute yourself. And if not, like, we can end this session. So, any doubts, anyone? So, no doubts. Okay, then. So, we'll meet in the next session, and we'll start with this color composite making step only. So we'll make true color composite and false color composite and then move on. So thank you everyone and happy learning. Bye bye.